Okay, everyone. Thank you all for being here today. I mean, some people are still walking in, but if you have not grabbed an agenda for today's event, you can just grab one by the check-in. And the lunch and the posters will be at 11:30. The posters are going to be outside, so right where you guys walked in. And lunch is going to be towards that way, to the left, as well as the breakout rooms. So all of the info has been updated on our website with descriptions for the speakers. So if you want like more details on one of the speakers that you see in the sheet, you can just go to ufdsi.com. And a little bit about the symposium. This is an event we've been hosting for the past decade probably. And if you don't know about DSI, which is the Data Science Club at the University of Florida, and we host this event as well as workshops and other events to promote learning pretty frequently. So I would like to introduce Jack Kendall. Jack Kendall is the co-founder and current CTO of Rain AI, a company building next-generation brain-inspired processors for artificial intelligence. Jack's mission is to build a brain bridging neuroscience, physics, and computing to reimagine how machines learn. His research includes highly cited papers on analog neural networks and neuromorphic architectures, and Rain is backed by leading figures in AI, including Sam Altman, the CEO of OpenAI. Jack is a University of Florida alum and one of the original founders and the second president of DSI, making his keynote today a full circle moment for the community he helped shape. Please welcome Jack Kendall.
All right, thanks so much. And hello, everyone. I'm Jack Kendall, right? I'm the CTO of Rain AI and one of the co-founders of UFDSI. I was actually planning on being at the symposium in person this year, but unfortunately work had other plans. So I'm calling in remotely from San Francisco. And today I want to talk about two things. One is briefly about what it was like founding DSI, and then I'll dive into a technical topic that's really at the heart of my research, which is the concept of computing in memory. So DSI was initially founded by a good friend of mine, Damian Chemness, and yes, Damian with an M. He was our fearless leader back in 2015, and I was introduced to him by a mutual friend who was also part of the co-founding group of DSI, Nick Herrera. And so us, along with a few other individuals, created the group that you know today. Unfortunately, Damian was graduating that semester, and so he passed the torch to me in the following semester. And so we officially registered the group as a student organization, and I served as its first official president. So thanks, Damian, for starting this whole thing. Our goal at the time was very simple. We wanted to bring the emerging tools and techniques of data science to the general UF population. And at the time, the only courses that were available on like data science or Python were within the computer science department, and a lot of those were actually locked behind graduate courses. And given that data science and data analysis and machine learning were all becoming increasingly important in all domains of science, engineering, medicine, we wanted to offer courses that targeted non-computer scientists. So we started a few introductory courses covering Python, statistics, and machine learning. These courses turned out to be much more popular than we were expecting. There was really a need for DSI, and it was apparent, especially with our introductory Python course. At the time, Python was growing really rapidly in popularity, especially within the STEM community outside computer science. And we were able to take advantage of the fact that no other course at UF was offering Python in a broadly accessible way. So it didn't take us long for us to realize that we had something special with this organization. We held our first symposium at UF that first semester when it was founded, and it was also a huge success. And it allowed us to connect students with researchers in the data science field at UF, which was, again, one of the things that we really wanted to do. So, as Matteo mentioned, this is like full circle back to where we are now. So with that said, congratulations to UFDSI on 10 years of success. I'm extremely proud of everything you all have continued to achieve with DSI, and I'm really excited to see where it goes in the future. So that brings me to the main topic of my talk today, and that's the idea of compute in memory, or how can we make computers more like brains? The idea here is that modern computer architectures like CPUs and GPUs separate where the data is stored, so the memory, and where computations take place. This is also known as the von Neumann bottleneck or the memory wall. Basically, you have to move this data back and forth across a narrow bus. And that's where all of your time and energy in processing comes from when you're running things like neural networks. So compute in memory is an alternative paradigm where you seek to unify memory and processing in a similar way as biological brains to enable massively parallel computation. So first, a little bit more about me and my background. So as was mentioned, I'm the CTO and co-founder of Rain AI, but I'm also a machine learning and hardware researcher. I have 11 granted patents on computer architectures for AI systems, over 500 citations in the machine learning literature. And my research focus is really on a few things. One is compute in memory. I also study neurobiologically plausible learning algorithms, so essentially neuroscience-inspired algorithms for machine learning, and then also analog computing. And I've got about 11 years of experience in the field. My ultimate goal really is to dramatically improve the energy efficiency of AI systems because I think we all know they're a little bit too power hungry right now. So I'll start off with a simple question. How do brains perform computation? It would be great if we knew exactly how this is done, but really what I'm interested in is how is it different from how computers perform computations? And there are a few important differences, and I'll highlight what I think are the most important differences. First, biological brains have these extremely high performance memory devices that are called synapses. And these synapses are arranged in 3 dimensions in a way that enables extremely high density. But not only that, they're also integrated in a way that allows them to perform computations as well. They also have dramatic advantages over modern computer memories in, for example, endurance and power consumption. And much of the advantages of brains are owed to the density and power efficiency of synapses. Related to this, brains operate much slower and with much more parallelism than computers. A typical computer, a single device might operate at a gigahertz in speed, so a billion cycles per second, while brains typically operate many orders of magnitude slower, around 100 hertz or 100 cycles per second. Right? So that's like a 7 order of magnitude difference. That said, brains are much more parallel, and they have trillions of synapses, at least in the human brain, that are able to operate fully in parallel. And kind of the last point is that our artificial neural networks, the ones that we build, they're really built on many layers of abstractions, from the physics of the transistors all the way up to logic gates, registers, programming languages, and then finally at the top layer, you have the neural network itself. And really at each layer of abstraction here, you lose some efficiency. And in contrast, in biological brains, the physical substrate is the network, right? There's no abstraction there. And brains use physics directly to perform the computations that they need. And we can take inspiration from this. And so this is something that I think is one of the big takeaways and one of the things that we can exploit to improve the efficiency of AI systems. So that brings me to analog compute and memory. And this is really the first successful method, I think, for combining a lot of these ideas. And what you essentially do in analog compute and memory is you construct arrays of artificial synapses, memory arrays of artificial synapses that are able to use physics to perform matrix multiplications directly inside the memory itself. And before we dive into how that works, I really want to illustrate the problem. This is a depiction of the memory wall, or the separation of computing and processing. On the left is a standard computer architecture, which contains the normal, usual memory hierarchy, right? So at the very top there, you've got NVM. This is like flash memory for storage, non-volatile memory. You have DRAM for main memory. And in neural networks, this is usually where the weights and the main activations live. And then you have SRAM for cache memory. And this is usually on the processor itself. And so you store chunks of data that you're doing immediate computations on in SRAM. And then finally, you have the processing elements or the arithmetic logic units or ALUs, where the computations actually take place. And each of those arrows represents a place where you need to move data back and forth. And that's where these are really where the memory bottleneck is in these buses. On the right, you see an in-memory computation engine. And in this, you actually do the computations, and usually it's matrix multiplication inside the memory itself. And I'll show you how that works in a moment. But the reason that we target matrix multiplication is because it's by far the most important, most common, and most time and energy consuming operation in modern neural networks. It's really where the bulk of the computation is in matrix multiplication. And I'll note here too that this is true even if you wanted to simulate biological neural networks. Matrix multiplication really is, it's just a proxy for how neurons communicate with each other. And so as the number of the number of connections grows, the number of computations grows with the number of connections in the network rather than the number of neurons, right? And so this is typically an n squared operation, right? So matrix multiplication is n squared in time. But compute and memory architectures are able to reduce the time complexity from order n squared to order 1. And in fact, you can do a vector matrix multiplication in one single computation step using this technique of analog in-memory computing. So how does this work? Let me show you how this is done. This is what's called a crossbar array, right? And in the crossbar array, you have three parts. The first part is where you put your inputs in, and your inputs are a vector, and you provide these inputs as a vector of voltages on the left here. In the center of the array, you have the matrix that you're interested in multiplying by this vector. And this is represented as the conductances of resistances, right? So you have an array, and at each cross point there in the array, you have a resistor, and that resistor has a conductance. And then you have your outputs. And this is another vector. This would essentially be the vector that you would read out after multiplication. And you read out these currents at the bottom. And apologies, I had amps there for a moment. Really, this is on the order of milliamps that you would want to be, or microamps, right? If you would implement this in a practical array. So really what we're doing here is we're using Ohm's law in matrix form, right? So we have a matrix of conductances. We provide a vector of voltages to multiply with, and then we read out the resulting vector of currents. And in this way, you can do the computation inside the memory in one step using physics to do the computation for you, right? And so this is the equivalent vector matrix multiplication that you would be doing. Now, if you want to do this in a practical way on very large neural networks, you're going to have to tile a lot of these crossbars together, and you're going to have to compile your neural network workload to take advantage of these hardware resources. So these are a couple examples of early actual data flow, full like AI accelerator architectures that use these ideas. So this first one is called Isaac. You can see it has a bunch of these tiles, right? And then within each tile, you've got a bunch of these crossbars, right? And that's the XB there. And you've got digital to analog converters, which converts your input data, and then analog to digital converters at the output, which converts your output data. And in the middle, you've got this analog matrix multiplication. And then you have Puma as well, which was a follow-up architecture. So people have really built pretty, I would say, sophisticated systems already, which use analog computing to do vector matrix multiplication in these types of arrays. But the current issue right now is really the memory devices that we have available for this are not great. They really can't compare in terms of density and endurance and even power consumption with biological synapses. So I want to quickly run through the memories because I see the memory devices as the biggest barrier right now to implementing these ideas at large scale. So you've got a few different types of memories that you can do this with. It can represent that kind of resistive crossbar. Um, you have two terminal memories, and this is like resistive RAM. So both of these architectures here are actually based on resistive RAM. PC RAM and MRAM, these are related technologies. Again, you're using a resistor as the matrix element to do the matrix multiplication. But you can also use capacitors too and do some like charge accumulation with them. Then you have three terminal memories, and the most important and most common three terminal element memory is NAND flash. And so I'll talk a little bit more about NAND flash and in particular 3D NAND. NAND is super high density, but it doesn't have very good characteristics in other respects. But you also have other types of emerging 3D memories, or sorry, three terminal memories like ECRAM, electrochemical RAM, and ferroelectric FETs or FE-FETs. And then lastly, you have SRAM. And SRAM is the highest performance memory that we have. It really is the best memory that we have in terms of power consumption, in terms of endurance and other characteristics, but it's very low density. It's very expensive memory. And it's good for doing small scale operations, matrix multiplications, but you just can't build like a billion parameter neural networks with it. You have to load the data into and out of the SRAM. And this is a good first approach, but ultimately we'd like to be able to scale these techniques to much higher density memories. So yeah, so the takeaway here is that there's no perfect memory for compute and memory applications, and we really do need future memory devices for large-scale CIM. So here I've got a list, and I'll kind of walk through some of the characteristics of these. SRAM at the top row got really fast read and write speed, really good endurance. It's volatile, but it's not as volatile as like DRAM, but the density is really low. You're really limited to like megabytes of memory. DRAM is known as main memory, or so it's also like GPU memory or high bandwidth memory. Um, this is where you store the model when you're running a neural network on a GPU. So you load the model into GPU memory or GPU DRAM or high bandwidth memory. You can store many gigabytes of memory in DRAM, and it's reasonably fast, has really good endurance, good density. The only problem is that it's super volatile. You store the state of the bit on a tiny capacitor, and that charge on that capacitor will leak off really quickly. And so you have to constantly refresh it. So that's why it's called dynamic RAM or DRAM. And you can kind of try and do compute in memory with DRAM, but it's difficult. And so I'll get into that a little bit later, but nonetheless, even though it's very volatile and hard to do compute in memory in, because of the other characteristics, I think it's actually a really good candidate for future compute memory applications. And then you've got flash, and the problem with flash is it's really slow to read. It's even slower to write. The endurance is very low, but its density is super high. I mean, you can think about like a flash drive that you can go buy at the store, like a thumb drive, and you can get a 2 terabyte thumb drive or more right? That fits in a chip that's the size of your thumb. And if you think about how many parameters that is, that's like you can fit trillions of parameters actually on a thumb drive. And if you could do computations in that, you'd really be able to, you'd have something extremely powerful. But because of these poor memory characteristics, it's really not practical to do right now. And again, I'll touch on that a little bit more later. Next, I want to move on to digital compute memory. Analog is great. You get really high power efficiency. You can do computations directly using physics. Um, but analog devices can be really finicky and they can be really sensitive to temperature and variations in manufacturing. Oftentimes, you really want to continue to do things digitally. Digitally just, digital just has this robustness to a lot of these effects that make it really appealing. And so you can essentially replicate the same process, the same overall idea in a completely digital fashion. And this is called digital compute memory or DCIM. On the left here, you see you can provide digital inputs just like before. And at the bottom, you can read out digital outputs. And then you can store your weights in SRAM, right, which is a digital memory. And so you can see that you've got these SRAM cells that store your weight values, and then they essentially connect to multipliers where your inputs come in. So you can multiply using these NOR gates, essentially bitwise, and then you can use an adder tree to accumulate those to get your output. So this is basically doing multiply accumulation. And what you're doing here is you're integrating in a completely integrated fashion SRAM with matrix multiplication circuitry in one array. Just to kind of show you, if you're not familiar with SRAM, what a typical SRAM cell looks like. It's 6 transistors. It's basically a pair that are connected in negative feedback that creates a bistable circuit. And on the left side of the figure here, you can see we've got like 4 bits of weights. So each bit would be an SRAM cell that would store 1 bit of your weight value. And you can essentially feed in your activations bitwise into these as well. This is kind of an architecture showing the structure of one of these DCIM arrays. On the left of the figure here, that's where you store your data. They're using a 12 transistor bit cell. And then that connects on the bottom left where your inputs are coming in. And so those go into a bunch of multipliers. You do your multiplications, your bitwise multiplications, you accumulate using this adder tree, and then you do some other processing like sign and shifts, and then you get your output. And you basically copy this a bunch of times, and you can do in-memory vector matrix multiplications completely in digital. So this can be done, synthesized using like RTL or like custom layouts, however you want to do it. But you can really get super high efficiency when you do this. And for a long time, the state of the art in doing matrix multiplications were these systolic arrays or MAC arrays, multiply accumulate arrays. And so like, in the TPU, Google's TPU architecture, for instance, they use multiply accumulate arrays and systolic arrays to do matrix multiplications. But DCIM, digital compute memory, has actually surpassed now the systolic array, the MAC-based systolic array for doing matrix multiplication. And it is the highest efficiency matrix multiplication technology that exists today. And you can see on the left column here, that's kind of the standard MAC array type matrix multiplication. And if you go down to the bottom where it says tops per millimeter squared and tops per watt, this is really 2 measures of compute efficiency. You can see that with compute in memory, digital compute in memory, you can basically 10x each of these, which is huge because again, matrix multiplication is the big driver of the computations that need to be done in compute memory array or in neural networks. Now, the other part of that is getting the data to and from these arrays, right, which you need DRAM for. Because again, that's where you're storing all of your model parameters. So what we'd really like to do is we'd actually like to start pushing compute and memory into higher memory density technologies. And I think going from SRAM to DRAM is the next logical step in this. Unfortunately, in DRAM, it's not practical to do the computations inside the DRAM cell itself due to the destructive read, and also, you can't really do custom DRAM. Like the memory manufacturers have tight control. They don't offer like custom design services like logic manufacturers like TSMC do. But what you can do is in each of the banks in DRAM, you can put a little multiply accumulation unit. So something very similar to this architecture here for SRAM, you can essentially copy paste that into each of these DRAM banks, and you can do computations on the DRAM die. And that avoids you having to move data into and off of the DRAM chip, which is actually where the bulk of the energy in time comes from in large neural networks, in very large neural networks. This is to differentiate this from like SRAM-based compute memory. This is usually referred to as processing in memory, or PIM. And this is a really exciting emerging field right now. This is from a relatively recent paper from 2023, which basically shows that you can really get 2 to 3 order of magnitude improvements in speed and energy efficiency compared to a GPU if you can do these matrix multiplications or multiply accumulations in the DRAM die itself, because you're reducing the amount of data that you've got to send from DRAM to your chip. The unfortunate thing is that in DRAM, the process, you really have poor kind of logic transistors and limited metal layers. But even with those constraints, you can get a big advantage compared to like GPUs. So the last topic I want to touch on is like, what are some future directions, some exciting new things that are coming out in compute and memory? First thing I want to talk about is like 3D memory. I mentioned at the very beginning that synapses are a 3D memory. And I think that's one of the really big advantages to brains, is that they can integrate memory in 3 dimensions. And that allows you to have much higher memory capacity. And the thing is that the larger the memory capacity, the more memory you have available in your compute and memory architecture, the bigger the advantage that you're going to have over von Neumann architecture, because it's less memory, it's less data that you need to move back and forth, and it increases the parallelism. Right now, those digital compute and memory engines, those are relatively small scale, but they're already beating von Neumann architectures like GPUs, and we're starting to see people integrate these into practical accelerators. Larger scale is definitely on the way. And so really right now, I see that there's this trend of GPUs, compute performance plateauing, and compute and memory architectures have already intercepted this curve. And so I think the future is going to really be based on compute and memory, for at least for neural network applications. So speaking of 3D compute and memory, I want to talk about NAND flash, because NAND flash is actually a 3D memory technology. If you go to the store and you buy one of these high capacity, thumb drives, it's 3D NAND. And basically you've got stacks, layers of transistors that are stacked on top of one another in like 100 plus layers. And each of those stores 1 bit, or technically a few bits. Again, like I mentioned before, you could really support trillions of parameters on one chip if you could do the computations inside the flash. But the thing is that computation in current flash memory is really difficult, and the devices have poor characteristics. So this is some work that we did at RAIN, and it's really on trying to imagine what a next generation memory would look like for compute and memory. And this uses the same exact manufacturing techniques as 3D NAND flash, but it uses RRAM, or resistive RAM, as the memory element. And basically what you do is you can have many layers, 100 plus layers of these memory devices that can actually be connected in arbitrary configurations. And you can see some of the connections here, in this in that top middle figure. But the idea is that you want to be able to replicate the patterns of connectivity that you see in biological brains. And this is a way to do that using existing manufacturing techniques. Now, one of the problems is that resistive RAM also is not a perfect memory device. There are still some issues with like endurance, and the manufacturing of this is challenging, but you would be able to do compute in memory in a chip that has hundreds, of billions of parameters in one chip. So I think this is the types of architectures that we're going to be seeing going into the future in maybe the next 5 to 8 years for neural network architectures. And this really does have the potential to improve energy efficiency of AI systems by like 100x. Another cool idea is doing, instead of vector matrix multiplication in one step, actually doing matrix matrix multiplication in one step. And so I think, maybe this is something like what brains are doing with this kind of frequency multiplexing. But what you can do is you can essentially use like the Fourier transform to split your input vectors into different frequencies and then sum them all together before you pass that signal through your crossbar. And what that will do is it will, instead of doing a vector matrix, it'll do a vector matrix multiplication for every frequency at the same time. And then you can split the output back into the constituent frequencies to recover the output vectors for each multiplication. So what this is basically doing is it's taking a matrix, multiplying it by another matrix in one step. And this is actually an order n cubed operation. So this really has the potential to, again, further increase the compute efficiency of matrix multiplications. Another cool thing that you can actually do is do matrix inversion in memory. And you can specifically solve linear systems of equations, which is normally an n cubed operation because you've got to invert these matrices. But you can do this in a single step using compute in memory. And it essentially uses analog conductance matrices with negative feedback connections. So what we're trying to do here really is expand the types of operations that you can do in memory and do things that weren't possible before because matrix inversion is an n cubed operation, it's really avoided in deep learning. But if you could reduce the complexity from n cubed to like order 1, that would make matrix inversion practical. And you'd like to be able to do matrix inversion in lots of places in deep learning. It's just too expensive right now. So this is a way to do that. And then there's also some novel algorithms that you can think about. And this is, again, some of my work with Ben Sellier, who is one of Yoshua Bengio's students, actually. But the idea here is that if you look at circuits, like electrical circuits, a lot of electrical circuits have this interesting property in that they're self-adjoint. They're basically the way that perturbations travel forwards through one of these networks is the same as the way perturbations would travel backwards through the network. And what this means is that they are able to compute their own gradients. And what I mean by that is you don't actually need to know anything about the network in order to compute their gradient. You can compute their gradient in a completely black box fashion. And that's different from how we normally run neural networks, which is we take this big computation graph and then we use backpropagation. And backpropagation requires knowing the exact derivative of the network. But in a brain, like one region of the brain does not have access to another region's weights, right? You can't, this is a problem with actually the mismatch between like neuroscience, how people think learning happens in neuroscience, and how learning happens in deep learning. And deep learning is widely agreed to be not biologically plausible because of the way that we compute gradients. So this is actually an explanation for how you might be able to do machine learning, specifically gradient descent like learning and optimization, without requiring backpropagation and in a way that is completely biologically plausible. So I find this to be super interesting, and this is a big part of my current research. This would essentially allow you to create super efficient learning algorithms for analog systems. And so that's everything that I have for you today. I'm happy to answer any questions, but yeah, thank you all so much again for inviting me here.
Any questions? Okay. Let me turn the computer around. Let me know if you can see me and everyone else.
Oh yeah, so the sort of question that I had is hi, can you hear me?
Yeah, I can.
Okay, so the question that I had is that, like the way I remember it from like my neuroscience class is that the brain normally, as you said, it has like local structure, which is neurons are like connected to a finite sort of other neurons, which means
Yep.
that the computations that happen in a brain could potentially be seen as like locally concentrated. Like the computations that a neuron will do will ideally be set up like concerned with like inputs it gets from its surroundings, which are fixed, like which are the set of neurons that it's connected to. But in our brain, like especially for like so not in our brain, my bad. In computers, you have like memory that's accessible by any part of the computer or like by the entire like memory block itself. So
Yep.
how do we like is that um like how do we handle that for like a memory that's trying to replicate how like the brain works?
That is a great question, and it's actually at the heart of this research here. So what you mentioned about locality is basically gradient descent is it's not a local learning algorithm. What it means is that one layer or one set of neurons, in order to get your weight update information, which is really your gradient,
Mhm.
it needs to have access to information that is upstream of that region of the network.
Mhm.
And that's what makes it not biologically plausible, is this non-locality of the update algorithm. This work here actually shows that if you use physics and circuits in the right way, you can make gradient descent local. You can make it a local update. And so you only require information that is directly accessible at the neuron in order to perform the weight updates.
I see. And
So,
another
so I
question.
encourage you to check out this paper actually if you're
Yeah, I
interested in this.
definitely
And some
will.
more interesting work has come as a result of this as well.
Mhm. And another question that I had is that, um, as far as you know, the brain computes things in an asynchronous manner somewhat.
Yep.
And our computers currently sort of struggle because, like we use the von Neumann architecture. So I also know about something called like a memristor that's being worked on. Do you have any sort of like simplified explanation as to how potentially computers could achieve that sort of asynchronous computation brains do?
Yeah. So actually, when I say RAM, so here, this bottom row, that's actually another word for memristors. And a lot of my early research was on memristors, or again, RAM is kind of the more recent word for it. There's some subtle like distinctions that you can make between them, but it's really resistive memory. And RAM can be seen as a kind of memristor. Now, as far as asynchronous versus synchronous communication, I think that the having asynchronous um, local communication is the right way to do things. And in fact, architectures like this are locally asynchronous. So the way that you would do, a matrix multiplication, or in this case, one of these matrix inversions, it's really the circuit that is computing all of the information locally. And so that's actually really completely asynchronous in the inner loop. But I do think that it's important to have things be synchronous at a higher level just because of the advantages that it gives you in terms of like compilation of network architectures. Basically, all of the machine learning systems that we've built are really built on synchronous communication. And so my argument would be that you actually want locally asynchronous, globally synchronous communication. Just to bridge, it's also kind of similar to my opinion on like analog and digital. I think you'd actually like to have local analog computation too, and then globally digital communication. But it's really about not just trying to mimic the things that we observe in biological brains, but instead to think about why they're there, why the brain makes certain choices, and to pick and choose the best things that brains do versus the best things that we are able to do, because we can do things that brains can't do. I think high frequency, communication is a good example of that. Like we have gigahertz that we can operate devices at, and so that might change the optimization, the optimal solutions. But anyway, that's kind of my opinion on synchronous versus asynchronous.
Hello. The question I had was related to like maybe future industry investment. So I currently do research.
Sorry, future what?
Yeah, future investment in the space. So I currently do
Cool.
research for neuromorphic computing, and I feel like one of the things I struggle with when I speak to people is like people think that this stuff is very far away. Jensen Huang made that funny little comment where he said quantum computing is like however far out. I feel like that has people a little scared. Who do you think are like the most maybe important investors in the space and making it big? Is it the chip makers themselves, like Micron, TI, and like Renesas? Is it people like Microsoft and Apple? Like, who do you think are the biggest players in mainstreaming this?
Good question. I'll give you kind of a hot take. And this really is a very recently developing thing. But right now, if you look at GPUs, NVIDIA, by far the most important component is the HBM, the high bandwidth memory. And this is the DRAM that I mentioned earlier. And it's the most expensive part of the whole system. And everything around modern GPUs, like Blackwell architecture, is built around integrating HBM, high bandwidth memory, with the accelerator itself, with the GPU itself. And the way that we do that is via an interposer. And so it's another silicon interface, right? You basically take two chips, your HBM chip and your accelerator, and you put them on top of another chip. And that serves as a communication link between the two. This is called CoWoS. And it's really expensive. And it's right now a major bottleneck in terms of memory bandwidth, which is very precious. Like everything in modern AI architectures boils down to memory bandwidth at this point, essentially. Now, what I see happening in the next few years is actually the memory manufacturers beginning to integrate compute into the HBM stack directly. This is a huge threat to NVIDIA. And the memory manufacturers are really excited about this. They're all doing really foundational research on like compute and memory and integrating computation into the memory stack. I think this is going to happen within the next few years, maybe by like 2028. So those are the ones that I would bet on. And they're the ones who I think are really investing the most heavily, big industrial players investing in compute and memory, and especially around like compute and DRAM. So that's my take. Take it with a grain of salt, but that's how I see things evolving. These are like at Samsung, SK Hynix, by the way, Micron.
Thank you very much, Jack, for the talk. Can you hear me?
Yep.
Okay. I guess my question is kind of similar to the point of like NVIDIA. I believe NVIDIA has somewhere out there say they have more software engineers than hardware engineers. Would you say your team at Ray AI is kind of more hardware oriented, or is there a distinction between the work that you're doing is like kind of the research on this, I'm guessing, is very hardware oriented, but do you still hire like kind of pure software, and maybe what's like the tech stack that we use to
Yeah, we do. So we have a full software team. The software team is mostly focused on compiler. And so building the compiler that maps your neural network workload onto the hardware itself in an optimal fashion. We also have an AI team as well. So we're really trying to integrate AI knowledge with very practical hardware design and compiler design as well. And then we also have kind of frontier research like this, matrix inversion and novel algorithms and stuff like that. And so this is mostly the research that I lead.
Hello, Jack. Thank you for taking the time to be with us this morning. It's so early as well.
All right.
So this question comes as you tell your story about being a part of founding DSI, and talking about your company and very interesting things. I'm wondering how, as a student, you bridge the gap from being in university and starting DSI to starting your company. Lessons you learn along the way, and I guess any advice that you might have for us students. So, thank you.
Yeah, so I can kind of briefly tell you about how that transition happened. And really it started in 2014. Really it started in 2013. I saw ImageNet happen it was the end of 2012. And for those of you that don't know, ImageNet was in my opinion, like the breakthrough moment for deep learning. It was the first time that a deep learning or neural network-based architecture achieved state-of-the-art in any kind of major field, and this was in computer vision. So there was this ImageNet challenge, which was basically a bunch of now low resolution, but at the time, like relatively high resolution images, and you had to do object detection across like 1,000 different classes. And neural networks, this architecture called AlexNet, managed to beat the state-of-the-art, and by not a small margin. It was a huge moment. And I saw that happen, and I was like, I'd always been interested in the brain and in neural networks in general. And I was like, oh my God, it's happening. Neural networks finally work. And I immediately knew that this was going to be huge. And so I was at the time thinking about like, what do I want to do research in? My prior research that I had focused on and what I wanted to go to college for was actually nanotechnology. But nanotechnology, after having done some research in it, it didn't really seem like it was ready yet. And I saw machine learning and deep learning as a much more promising opportunity. And so I decided to kind of change track to that and kind of neuroscience. And I wanted to use the experience that I had in hardware in order to inform this. So I became obsessed with understanding how the brain worked and trying to think about I made a bet that hardware was going to be the limiting factor for AI at the time. And so my question was, how can we improve our hardware architectures? That's when I got into like compute and memory and thought about like what are the big advantages of brains and how you might do that. So 2014, long story short, 2014, I filed my first patent, and it was on a compute and memory architecture using nanowires. So it was a pretty out there idea, but it really had a lot of big advantages over what people were currently doing with crossbars. And it attracted some external interest. So basically, some investors reached out to me and said, UF helped with the publishing and the patent application process and everything. They published it on their website. And then that's how these investors found it. But they wanted to help me commercialize this idea. And so at that time, I was already really interested in starting a company. And basically my two options were, do I go get my PhD or do I try and self-fund this research and start a company? And I chose the latter. But yeah, so that initial seed investment was really critical. And then I got a friend of mine, his name is Gordon, he was actually the second president of DSI, to go in on this with me. And he served as the CEO, and we got some funding. we went out to San Francisco, we met Sam Altman, and he decided to invest, and that was like a huge moment for the company. Like we got really lucky with that, to be honest. So yeah, that's kind of a breakdown.
Hey, can you hear me?
Yeah.
Okay, so the main thing that I'm noticing about the architectures in specific is that there's this notion of static connections being made. So it's not really dynamic in a sense where you can choose or alter for example, the array length that you're using. How do you guys plan to address this? Because I feel like that's where GPUs might have the advantage.
Um, so you can dynamically allocate. It's really just about splitting. It's about allocation of matrices. And so if you go back to, let's see, this is a good example. Again, all you're doing is matrix multiplication, and you can actually map the matrices dynamically onto these tiles. So if you look on the left side, the T copied here, you can write different matrices to those arrays, and that can be done dynamically. And so you can do anything in a GPU, anything that a GPU can do, you can do in this architecture as well. So for example, this is also what TPUs do, right? But you just need to be able to dynamically change the values in the array. Now, different memories are going to be able to do that to different levels. And one of the big disadvantages of resistive RAM or memristors, RAM, is that you can't do that very frequently or very many times. So the endurance is limited and the write time is quite high. That's where SRAM shines. And so that's why this is really state of the art, because you can change the weights of this matrix and dynamically allocate very fast and very efficiently. Now, if you want to have your weights be completely static, then that becomes a challenge. And these are called data flow architectures, where you kind of want to map the matrices in a static fashion. Usually this is very good for like the slower memories. So like if you wanted to use Flash, for instance, because the read and write speed is so slow, you'd have to keep those, you'd have to just kind of pre-allocate those matrices and not switch them around. So in that case, your connectivity would be fixed. And that's one of the big disadvantages of them. But I still think it's possible. You can kind of mimic the dynamic connectivity by just setting certain values to 0 and turning them off and on or using switches. So I think there are ways around it, but that's kind of a quick summary.
We have time for one more question.
Kind of moving away from the hardware aspect, as far as neuroscience, what next topic do you think that research requires of neuroscience in order to move past whatever hardware roadblocks that you're running into right now?
To be honest, I think it's the way that we do optimization learning. Now, I do also want to say that I think this might be an unpopular opinion, especially I think in the neuroscience community, but I actually do believe, and I've studied this really deeply, I do believe that modern AI architectures are actually really close to what brains are doing. It's not the exact thing, but the most important things that are happening within the network itself as it learns, I think is actually shared. And the big difference, there are two major differences, right? One is the compute efficiency with which brains operate. That's this hardware thing, right? But the other thing that's different is their data efficiency, right? Brains are much more data efficient and they seem to learn in a fundamentally different way. My opinion is that what brains are doing is actually second order optimization, not first order optimization like backpropagation. And I actually think that it's connected to this idea here on matrix inversion and the fact that we don't use matrix inversion in deep learning. But in order to do second order optimization, you actually need to do matrix inversion. But hardware kind of, and again, if you exploit these techniques, hardware kind of gives you matrix inversion for free. And you might be able to implement second order optimization very efficiently in hardware in a way that actually looks like the structure of what we observe in neuroscience. It's connected to this idea here, but this is really the heart of my research right now. And so my opinion is that when we figure out how brains, I really strongly believe that this idea of in machine learning that has become so dominant, which is like learning as a form of optimization, optimizing some objective function. In the case of neuroscience, it would be reward, right? You're optimizing your reward signal, which is dopamine. But optimization, learning as optimization, but instead of first order optimization, it's a way that we don't currently understand, but like of doing second order optimization, which would make learning much more efficient. And it would actually look a lot more like what neuroscience, what biological brains are doing. So that's my take, is it's not actually so much the neural network architectures themselves as the way that we do learning. And I think once we understand how STDP, spike time independent plasticity, like we know that's how synapses change their strength, but it doesn't tell you, we don't actually know anything about globally how these weight updates are being coordinated. So STDP is not a learning, right? It's a plasticity mechanism. And I think that's lost on a lot of people in neuroscience, right? This difference between, okay, yeah, I can know how a synapse is changing its strength based on the two neurons that are connecting it, but what is providing that learning signal, right? You have to go through this complex chain of, neurons to get from your dopamine release to actually assigning credit. This is called the credit assignment problem, by the way. So I think solving the credit assignment problem in neuroscience is the next major step. Once we understand that, I think everything will fall into place, actually.
Thank you.
Okay, we're right on time. Love to thank you.
Perfect. Okay.
Thank you very much, Jack, for your
Yeah,
time.
thank you all so much. Yep. Have a good one. Bye.